So the second part we're looking at today is the combination of uniformly distributed load as well as point loads. Now this is called a UDL because what you can see there is a load which is not concentrated at one point, but it is spread across a distance. By how much? By a certain amount of force per unit length. So normally, you find that this uniformly distributed load is normally presented as newtons per meter, kilonewtons per meter, meganewtons per meter. In other words, it's just about the length, then how much force is acting per unit length, hence the uniformly distributed load. But then, in most cases, you will not just have a UDL. In practice, you find a combination of a uniformly distributed load as well as point loads like we have here. If it's purely a UDL, case is slightly simpler because you're just going to look at how it behaves and you start the analysis from there. Having said that, I wanted to segment. If you look at the letters from A all the way to C, you can see that this left-hand side, they are all point loads. But the moment you move from C, going forward, C up to E, it's under a UDL. But unfortunately, there's also point loads that are acting there. So we'll try to understand in our question, in this question, I want you to take time to look at how we're going to handle this, considering that this one is not just the point loads, but you have these uniformly distributed loads that are actually acting within the same point loads. So a combination of those, how a scenario can come out. So it will start with the analysis, and later on, we'll also go to the from the analysis, which is about the population, then we'll go to drawing a graph, which will represent what is happening here. So our question here says, the system shown in the diagram below is in balance under the action of the concentrated loads and the uniformly distributed load. Determine the reactions and draw the shear force and bending moment diagrams. So two things that we need to do. First, we need to find the reactions, which are R1 and R2. Then after that, we need to to calculate the shear forces, later on the bending moments, and then draw the diagrams. But the question simply goes straight to the point, like we had mentioned earlier. When they say draw, you cannot draw from these numbers. You need to calculate what are the shear forces, what are the bending moments, then you proceed to your drawing. So as per practice, let's start with the first one then. We're going to look at, first of all, the reactions. So this is the graph, this is the diagram we're looking at. Now we can decide to take moments either about R1 or we can choose R2. Whichever we choose, the principle still remains the same. So in this case, we are saying we're taking moments about R1. Let me just quickly move this. Sorry, that's R2. We're taking moments about R2. What principle are we applying? We're saying summation of clockwise moments is supposed to be equal to the summation of anti-clockwise moments. This is the principle. Where is R2 in this diagram? It's here on the far right. And one thing you realize is that if you have a graph like this and the reactions, one of them is not inside there, it usually makes your work much faster when you're finding the reactions to take moments about the one which is at the far end. That makes your work slightly faster with less complications, with less mistakes that you may make. If you see reactions like this, you can use them. But here, there's a chance that maybe you may make a small mistake here and there. You just have to be very careful as you do that. But unfortunately, there are some questions that the reactions are both inside. Then the forces are the ones working even on the outside. There are still other forces on the far end, but the reactions are there. So here we are, taking moments about R2. Condition for moments, summation of clockwise moments is equal to summation of anti-clockwise moments. With that, we pick up then. We're saying, first, which are the clockwise moments? There is 20 multiplied by the whole of this distance, which is 2 plus 2 plus 2, which is 6, and then you add 4. In other words, 20 times the whole of this distance. 2 plus 2 gives me 4, plus 4, that's 8. Again, plus the last part, which is 2 meters here, that's 10 meters. So hence, I'm saying 20 multiplied by 10. Now, one thing you realize is that this 20 times 10 is actually giving me an anti-clockwise moment. The same thing is with this, all these forces that are acting downwards. The moments that they're producing, the moments that they are having are all going to be anti-clockwise. The next one I look at is 80, where you can see 80 here. Since I'm taking moments about R2, I look at the distance from where 80 is and where R2 is. I realize there is 4 and 2. So I'm talking about 80 multiplied by 6, because that's 4 plus 2. Let me go through that again. The second anti-clockwise moment is this one here, 80, which is acting downwards. So what do I have? I can now say this 80 multiplied by the whole distance up to R2. What is that distance? I can see that this distance is a combination of this plus this. I'm talking about 4 meters plus 2 meters, giving me 6 meters for the 80 kilonewtons. So I have 80 multiplied by 6. Next, I continue. I come to the UDL. In the UDL, what I have now is 10 newtons per meter. Now, what am I going to do? Whenever we have a UDL like this, what we expect is that the whole of it is concentrated at the center, here at the center. Now, considering that this is the UDL is only covering 4 meters from there to there. What is the center of 4 meters? It's half of the 4, which is 2 meters. Therefore, I'm going to multiply this 10 by the whole distance I have here, which is 10 times 4, to get a force. When I multiply 10 times 4, the meter will cancel out, I get a force. But I also need the perpendicular distance from R2. The perpendicular distance will be measured from point D at the center of the UDL up to R2. So I say 10 times 4, it gives me the force. Then I now look at the distance, which is now running all the way from here to the far end there. And what do I have? I can see there's a 2 here. And I also know that half of 4 is 2. So I'll add this 2 and that 2. So hence, we include 4. Let me go through this again. What we're saying is this. I want to get the force, which is 10 multiplied by 4. How do I even know that? Because the moment I multiply 10 newtons per meter, so I'll say Newton per meter, that's our UDL. Then I've multiplied it by what? By 4 meters. I've multiplied it by 4 meters. So what you see is that this meter cancels out. So I have a force, which is more like just a 40 newtons. Now that force that I'm having, I also need the perpendicular distance because I am dealing with moments. And that perpendicular distance should be from the center of this, which is at point D, going to the far end. So the center of 4, the total distance where the UDO is 4 meters. What is half of 4? It's 2. So since I have 2 meters from point D to point E, I can already see that there's also another 2 meters from point E to F. Then I can add 2 plus 2, giving me the last 4 for this. So our combination is that the first part here is giving us the force. The last part there is giving us the perpendicular distance for this moment. I'm not done. I also have the last one, which is this downward force. So I'm saying 40 multiplied by that distance up to R2, which is 2 meters. So this is the 40 multiplied by 2 you see there. All these we've been talking about are basically just anti-clockwise moments. Let's talk about clockwise moments. This is our fulcrum for now. This is our fulcrum. This is our 0. This is the point at which we are taking moments. This is our reference point. So meaning that any force acting there, we will not consider its moment because the distances are being measured up to there. If you notice in our working, the only one I didn't include is this for a reason, because this one is the only one which is going in the opposite like that, telling me that this is now a clockwise moment. So I'll say R1 multiplied by all that distance up to R2. By inspection, you can already see that from R1 to R2, the distance that I have is 2 plus 4, which is 6, again plus 2, giving me 8. Meaning I have now R1 multiplied by 8 as the distance. So this is what we have here for the other side for the clockwise team. Let's proceed. With this, we can do some algebra. The multiplication there, the first part gives me 20 by 10 is 200, 80 by 6 is 480, then 10 by 4, 40 by 4, giving me 160. Next, I also have 40 times 2, which is 80. On the other side, it's 8 multiplied by R1, giving me 8 R1. So that's the expression I have there. Next, I can take it now and make R1 the subject of the formula. And the answer I have is 115 newtons. Then what I have now, I can decide to take moments about R1 in order to find R2. Or, because I've already got R1, I can just go by the shortened version, which is what you see here. Summation of forces acting upwards should be equal to the sum of those that are acting downwards. Which forces are acting upwards? I can see there's R1 and R2. So if I decide to add R1 and R2, this should be equal to adding all the forces that are pointing downwards, starting from here, this 20, 80, the UDL, and the 40. Let me see that then. My upwards forces are just 115 and R2. Here, don't worry, just switch them deliberately somehow to even test your understanding. The downwards forces, you can see, there's 20, 80, then the UDL. The UDL we're saying is supposed to be 10 by the total distance, which is covered by the UDL, which is 4 meters. So we have 10 multiplied by 4. Plus, we still have another force here acting downwards. That is 40 newtons. So I have 20 plus 80 plus 10 by 4 plus 40 being equal to the upwards 115 plus R2. In other words, Why we've written 115? Because this is basically supposed to be my R1. It is my R1. R1 is the one we found here, and it's an upward force. So from there, we can do the algebra. We will notice that on one end, here, when I add everything together, I end up with a 180. So this 115 can go to the other side. So I will have 180 minus 115, giving me 65 newtons. Notice one thing. We do not rush this part. This part is never to be rushed. When you are doing engineering science in your first level, I think in the old syllabus, for those of you who did the old syllabus, the science that you did, part of it even continued in your second year. But what you did in your first year, this is where you would end your analysis. You were just able to calculate the missing forces, just the reactions, and you end there. But here, this is where our work begins. So when you're calculating these, we are going to use them where the next part of the work, including the last one. So if you've made a mistake with the reactions, don't expect any miracle to come now with the shear forces. That miracle will come with you failing because you are already in the wrong direction. So you make sure that the reactions are correct. That's when you proceed now to the shear forces. Is there a way of proving? Yes, there is. The same way we've said summation of upwards forces is equal to summation of downwards forces. This statement we've put up here does not tally if this is wrong. Plant your numbers and put here, put R1, R2. The answer you have here and what you have there, they should be the same. Either way, now that we are done with the reactions, let's start with the shear forces. The shear forces. Again, you can see, I want us to be referring back to the diagram because this is what we're looking at. This is the one where this is the one we're trying to analyze. So with the shear forces, I'll be very careful because this is the combined kind of loading. Where there's just point loads, I will focus on the fact that the part with no load, the unloaded portion is normally subjected to uniform shear. So I'll move A to B, B to C. Then when I reach C, I'll have another force there. We'll see how we're going to do this. So let's get to work then. Shear forces. A to B. For those of you who like mathematics and you like using letter X as your variable, here you could already say 0, X representing from 0 to 2 meters, representing the distance. So I'm talking about from A to B. Usually for me, I find it smarter to pick A, B, those letters, but the interpretation is basically the same. So from A to B, you are standing at point B. Looking on the left, ignore what is where you are. This is your headquarters. This is where you're putting your foot. When you step on something, you can't see it. So A to B, when you look back, you notice there's only one force, and that force is acting downwards. We said that forces acting downwards, remaining on your left-hand side, are able to, or they account for negative shear forces. So your answer here comes out as therefore negative 20. All right, let's try then. B to C, we are doing the same thing. From B to C, I'm setting my foot at point C. Looking back, this side, which forces do I see? I'm already able to see 20 acting downwards. I can also see R1. Let me give it a number. We say the R1 is a 115. And we also say the R2, oh, sorry, forgive my handwriting. R2, we said this is 65. So this is our 65, 65 newtons. Now, following the same conditions, following the same principles, this force is pointing downwards. telling us that it's negative. 115 is an upward force, representing positive. So the two of them are standing side by side like that. I have negative 20 plus 115, giving me 95 newtons. Now, there's so many methods you can do this, but the method that I prefer to encourage you to use is one that doesn't stress you to start wondering, where is this number coming from? Why has this come to this, and so forth. And I think this is the one I usually try to stick to. Here, I'm now done. My answer when I say negative 20 plus 115, it's the same as saying 115 minus 20. 115 newtons minus 20 newtons. What do I get? It gives me 95. Then at the same time, here I'm now going into the UDL. The UDL is tricky because it's not at one point. It's spread across the whole of that distance. So when you're entering the UDL and you have a point load, you respect it. You say first slightly after point C, just after point C. Meaning that we expect to see two answers for point C because we're transitioning, we're just entering into the UDL. So how am I going to represent this? I'll write it in this way. I will say at point C, or if you were using the letters, you're using this variable x, it even becomes smarter because you say x is less than or equal to, meaning just slightly after this point C. Now, what are we trying to achieve? Here, all the forces when we calculated earlier remained on the left, except this one. So when we say slightly after point C, this is the one we're now calling, we need to calculate also at point C. It is going to include this force as well. That's all. So you found that answer. But here, get another one where you should also include this. Even if we had the UDL running all the way here, we're going to do the same. At point C, we were going to have, first of all, the answer you get without including this one, and the answer you get with this one included. Two values. Because at this point, you are transitioning, you are having both the UDL and the point load. So then what are we saying? We're saying on the left, then we have negative 20, which is acting downwards, followed by upward force, which is 115 positive. Next, this newcomer, 80 newtons, and it's acting downwards, telling us that this is negative 80 newtons. So when you add them, when you enter this in your calculator, you get 15 newtons. Because after all, these negatives give you 100, so 115 minus 100, this is it. So 15 newtons. Now, here, you are not mandated to have point D. Deliberately, we include point D for the accuracy of your answer, for making sure that when you come to the drawing, you're not going to get lost, you're not going to find it tricky. So this is point D in the middle. So what are we going to do? Since this is your point D, this, we also need to know what, we will take point D as also another point. So what happens at point D is now interesting because you are splicing up this UDL, taking only half of it. Next, you come to here where you're going to take the whole of it. But first, you are here in the middle where you've only taken half of the whole UDL. So what are you having? From point D, the distance is 2 meters because this is 4 meters. Therefore, from here, going to the center, you have 2 meters. So how do you get the force for this one? It's 10 times that same 2 meters. It's a downwards force, so it's going to be negative. Next is negative 80. We have positive 115 and negative 20. In that order, or like this. So here I'm at x is equal to 6 or 6 meters from the left end, which is point D. This is where I'm saying I have negative 20. I have positive 115. I also have negative 80. And the newcomer, which is now the UDL, 10 multiplied by 2. So 10 newtons per meter times the distance that I now have because I'm just here and I'm looking at what is remaining on the left-hand side. So 10 multiplied by 2. 10 multiplied by that distance there, which is 2. And then I get my answer, 5 newtons. Let me proceed next. I'm going to proceed to point E. And this is smart now. This is smart because we're just about to come out of this and you'll see why. Point E, we're saying it is at this point where x is equal to 8. So I'm going to look at all the forces remaining on the left-hand side. All these on the left, except the one which is where I'm standing. So what do I have? I have negative 20 plus 115. 115 is positive. 80 is also negative, so that's negative 80. Then since I'm at point E, I'm going to use the whole UDL, 10 multiplied by the whole distance, which is 4. 10 multiplied by 4. And it's negative because it's acting downwards. And what is my answer? Negative 25. Let me go to the last one. E to F. Now notice here. Did you notice that we already calculated for point E? Again, we're saying E to F. This is the behavior we're talking about for UDL. When you're coming out or you're going in, you expect 2 answers at that transition point. So what do I have now? I have this negative 20. This is positive 115. This is also negative 80. This one I'm also going to use the whole of it. So I'll say negative 10 by 4. And lastly, I should have 40, which is also down, also negative. So that's what I have there. I have negative 20, positive 115, minus 80, minus 10 by 4, then minus 40. My result is 65. Now, here is your first checkpoint. When you are on the right track, for a normal UDL like this one, without special cases, I think in future, one of the exam questions we're going to look at to have something interesting that defies that rule. When you reach here, the answer that you have there should be whatever value you calculated here. So we are at point E to F, the last region, there, 65. And it's negative, although we know our reaction towards positive was 65 acting upwards. But that is the way the sign convention is when you look at, if someone had to start calculating from the right going to the left, he will reproduce these same answers because the sign convention will be the other way around, but reproducing these values as they are. So that is your 65. And these are the shear forces. Again, if you want to get this right, you make sure that all those answers are correct. As long as the reactions were fine, here also you don't rush. You make sure that all is right. That's when you can say, let me go for the shear forces. Hence, we proceed for the bending moments. For the bending moments, things are very simple because we move point by point. So I'm at point A. Here, my distance is 0. So what am I going to have? I'll have negative 20 multiplied by 0. Now note, if you want, for those of you who are really mathematical, you can take variable x to represent the distance to represent variable x. So that as we keep changing, here you'll be putting 20x and then it continues. But the analysis is still the same as what we'll still do here. Proceed to point B. When I'm at point B, I have this negative 20 multiplied by 2, because now x is 2. So negative 20 by 2 equals, we get our negative 40. Let me proceed to point C. Point C, you can already see that I've left 2 of the moments on my left-hand side. The first one is negative 20 by the whole 4 meters. Then I also have positive 115 by 2 meters. Negative 20 by the whole distance up to point C, which is 2 plus 2, giving us a 4. Then the R1, which is 115, I can already see that where there's R1 and where there's C, the distance I have is just 2 meters. So that's how come 115 multiplied by 2. Then I proceed now to point C, or rather to point D, the one in the middle. When I come to point D, again, it's the same thing. I just realized that point D is here at the center. So what I'm going to remember is that this UDL, we're only cutting 2 meters of it. And this is where we'll remember to say that distance, when we cut the distance, any uniform material or a UDL, the UDL is concentrated by its center. So since we're talking about only 2 meters, it means the center of the 2 meters will be half of the 2 meters. But let's see what happens here. I'm at point D. The distance from where 20 is and D is 2 plus 2 plus half of 4, which is 2. That's where you can see negative 20 multiplied by 6. If I go to R1, it is 115 by this distance, 4, which is 2 plus 2 there. Positive 115 by 4. Next, I have this UDL, which is 10 multiplied by 2. Oh, sorry, before I get to there, there's 80. So there's 80 times the distance here, which is 2. But as for the UDL now, to get the force, I multiply 10 by 2 meters because for now, I'm just consuming the 2 meters. I'm not yet away from there. I'm just at point D. The perpendicular distance will act at the center of the 2 meters, which is half of 2, giving us 1. So it's 10 by 2 multiplied by 1. So when you enter all that in your calculator, you end up with 160. Then I proceed to the next point, which is point D, oh sorry, point E, the last end of the UDL. So for point E, I'll say all these remaining here, the first is negative 20 by the whole of that distance, which is 2 plus 2 plus 4, giving us 8. So x is now 8. Negative 20 by 8 plus, this is the one you say x minus 2. So this is now 115 multiplied by that distance there, which is 6. Next is 80, which is also negative, by 4, because this is from there all the way to there. Then comes the culprit. Here I have 4 meters, so I'll multiply 10 by 4 to get the force. Again, I multiply by half of 4, which is 2. So 10 multiplied by 4, again multiplied by 2. Where is the 2 coming from? Because this UDL, the total length of the UDL, where the UDL is active, is 4 meters. What is half of 4 meters? It's 2 meters. So therefore, I multiply this 10 by 4 by that 2 meters, which is running from D to E. So 10 times 4 and times 2. Your calculator should lead you to there. Now you have 130. Here's our next checkpoint. Remember, when we started, our answer for point A was 0. As long as, again, this is not a special case, like the way some of those loadings can be. This is at rest. There's nothing unbalanced. We expect the same answer we started with to also be the same answer we end with. So I'm going to the last one, which is point F. When I go to point F, everyone is involved. Our variable, our total distance for X is 10. So meaning that negative 20 by 10, where is the 10 coming from? My negative 20 is here, acting downwards. Then this is where F is. To get the total distance, I can add all these distances. I have 2 plus 2 giving me 4. 4 again plus 4, that gives me 8. Again, 8 plus 2, it gives me 10. So that's what I have now there as 10. Next is this 115 multiplied by x minus 2. In other words, the difference between them is that this one is just lagging by 2 meters, so we remove the 2. In other words, or rather the other way around is, this is 115 by this distance in between. If you look at that distance, it's just adding what is there. It's 2 plus 4, which is 6, plus 2, giving me the 8, which I have here. Next, I introduce the 80. So this is 80 multiplied by this distance here, which is 6. So negative 80 times 6. And then I have our favorite, the UDL. The UDL is 10 multiplied by 4. 10 multiplied by 4. Then to get now the distance, I'm going to get, because the UDL is acting at this center here. And I know that from where D is, which is the center of the UDL, to E, it's a half of this length here, which is 2 meters. So I'm going to add this 2 meters, and that's 2 meters, similar to what we did during finding of the reaction. So I'll say 10 times 4. This is just helping me to get the force. Then the span, the perpendicular distance is now going to be times the last one, which is 4, because it's from here, D, up to F. So that is times 4. Lastly, I'm saying take away 40 multiplied by 2. That's negative 40 by 2, because the distance here is just 2 meters. When you enter this in your calculator, and though your reactions were correct, you expect to get a 0. You expect to get a 0. Like I said, this 0 should only come out if this is not a special case and your reactions were correct and there are no hiccups along there. Let's pick up the next one then. Here, we've done the calculation of both the shear forces as well as the bending moments, but there's still one thing that is remaining. The question was not even asking us to calculate this. It was asking us to draw. By implication, it had also requested us to calculate, because you will not draw without calculating these values. Here goes our drawing. If you look at the reactions, the numbers that we had, first, as per tradition, when you're drawing the shear force, you reproduce the diagram in the question the way it was. Then below, you start with this neutral axis. And up here, this is the positive region. This is the negative region. So from A to B, the answer we got was negative 20. From B to C, we had 95. At point C, we also had 15. Same thing with point E. Point E, we also had 2 values where we said, sorry, it's going somewhere else again. Yeah, so for point E, we also said there was 25 as well as 5. For point E, and also E to F. Yeah, here we had 65 as well as 25. So this is why when we come to the drawing, we replicate that. So this is 65, and that is the 5. Same thing. For the bending moments, we're moving point by point. At point A, we had 0. Oh, sorry. After you get those, it's just about closing the boundaries where the numbers are. There, there, there. And where we have two answers, two numbers, we plot them like that. The first number and the second number. Even if it was a negative, we could have come to where it is and we continue. And then we continue. Here we also have the 1 for point D, which was -5. So this is our -5 here and that. So we connect them using straight lines and we close. Then we can shed or just leave the boundaries. When we come to the bending moments, point A, it was 0. Point B, we had -20. This is -20 kilonewton meters. Oh, sorry, in fact, it was -40 because it was -20 by 2. -40 kilonewton meters. Then we proceeded to point C, that's 150, point D, 165, point E. So for you, during that time, you could just be putting my dots, just the dots. The last point is where you see a 0. And the 0 takes you back to the neutral axis, that axis of the beam that you drew before you started. Always check that you have enough space up here and enough space below there. If you don't have enough space on the cover, on the page where you're writing, proceed. Get enough. Go to a fresh page and start your working. Then you'll just be okay. So this is how you handle a uniformly distributed load when it is mixed with a point load. And since we're just getting started, as we pick up some of the question papers, some of the questions that have come there, we'll see how we can also apply the same principles on different case scenarios. For now, I have an exercise for you here. Believe you enjoy working on this one. All the best as you enjoy doing just that. As we practice, feel free to link up and send me a message in case you need to clarify something. Or you can always put a question in the comment section. I'll respond as soon as I see it.